Okay, in this chapter, we'll talk about natural radioactivity, different forms of radioactive decay, the applications of using radioactive tools in research. Radioactivity comes from unstable nuclei, which are found in elements with atomic numbers 20 or higher. Radioactivity is defined by, in nuclei, the nucleus can't keep itself intact anymore, and the forces of repulsion outweigh the attractive forces. So these nuclei will emit particles of energy, small particles of energy. This is called radiation. And this is done so to become more stable. Now, radiation will take the form of different types of particles, alpha, beta, positrons, or pure energy such as gamma rays. And you see these symbols here, alpha, here then beta, and then positron, same symbol as beta but with a plus sign. And then gamma rays looks like a lowercase y. Those are the Greek letters. A radioisotope, this is an isotope, something we've already talked about in previous chapters. Isotope of an element that emits radiation. And there can be one or more isotopes of an element. And the radioisotope will include the mass number in its name. That's a way to indicate if something is a radioisotope or not. Alright, the example that's given is iodine. Normally the way to represent iodines with a capital I is atomic number is 53, but its regular atomic mass is 127. So if you were to name an isotope of iodine, you would include the mass number in its name. There are many forms of, or many different types of isotopes of iodine, but a very commonly used one is iodine 131. This is a radioisotope that's used to help diagnose and treat thyroid disorders. Though it still has the atomic number 53, it's still iodine, but the mass is different because it is an isotope of iodine. It's a radioisotope. That's why it's indicated by calling it iodine 131 and not just iodine. Here's a table of some stable and some radioactive isotopes. For stable here, magnesium 24 or iodine 127. Some radioactive forms, magnesium 23, magnesium 27. These are still forms of magnesium, but they have different masses, so they're isotopes, and because they emit radiation, they're radioactive isotopes. And for iodine, normal form is 127, but 125 is an isotope, and iodine 131 is an isotope, a radioactive isotope. And then uranium 238. And 235, different forms of uranium. There are different types of radiation depending on what kind of particle is being emitted. We talked about alpha, beta, positrons, and gamma rays. The alpha particles, these are identical to a helium nucleus. That's why this is here. The symbol for helium, He, atomic number 2, and the mass is 4. These values will be important later on in this chapter. Beta particles, these are high energy electrons, or these emit high energy electrons. This is how that's indicated. E for electrons, -1. Positrons, that's a same thing as beta, but positive form. And then the gamma rays, the symbol for gamma, and the zeros for here and here. Here's a summary of the different forms of radiation, and their symbol, and then how they're written, and then how it changes the nucleus, and how it will change the charge of the element. For example, the alpha particle, of course, the symbol, again, identical to a nucleus of helium. And you'll have 2 protons and 2 neutrons are emitted as the alpha particle, and it will change the mass number of the element and also change the atomic number also. And the same goes on for beta particles or positrons or gamma rays. This table is really just this information but in a table form. Alright, nuclear reactions. In a nuclear equation for alpha particle decay, the mass number will go down by 4 and the atomic number will go down by 2. And these numbers are not random. Remember we talked about the alpha particle is identical to a helium nucleus. So that's why when you look over here, if you're looking at a radioactive uranium nucleus, when that breaks down and starts to emit radiation, what it emits is something that's identical to a nucleus of helium. So again, when you're looking at these notations, the symbols here, atomic number here, atomic mass is here. Well, when you lose energy and lose mass, it doesn't just vanish. There has to be a conservation of both of those components. So what you're doing is you're changing the element that you started off with. The atomic mass totals don't change before or after, and the atomic number totals won't change before or after the decay. That's what this image is showing, and that goes back to the learning goal for this part of the chapter, being able to write a balanced nuclear equation showing the mass numbers and the atomic numbers for a radioactive decay. And that's what this image is showing. Starting off with uranium, the radioactive uranium nucleus. Atomic number is 92, mass 238. When that breaks down, it will, because it's alpha decay, it will release something that has atomic number of 2 and a mass of 4. Well, that's going to change these two numbers here. That will go down by 4. So now instead of having 238, you have 234. And the atomic number will go down by 2. So instead of being 92, you have 90. Well, when you change the atomic number, that changes the element completely. So now you have thorium, which matches the atomic number of 90, and the mass will be 234. So when radioactive uranium breaks down with alpha radiation, what it emits is an alpha particle, and the result is also thorium with a mass of 234. But the totals don't change. If you add this mass and that mass, you get what you started off with, 238. If you add this atomic number, 2, and that atomic number, 90, you get 92, what you started off with. These masses and these energies don't just vanish. They have to be the same before the decay and then also after the decay. So in a radioactive decay, the nucleus will break down when it emits radiation. And we're just talking about alpha decay in this example for the uranium and the one that's on this slide. There are other forms of decay, beta, positrons, gamma rays. Those all affect the radioisotope differently. But right now we're just talking about alpha. So for example, this element here, CF, is californium. The atomic number is 98. Its mass is 251. When that breaks down with alpha decay, the atomic number will go down by 2. So that gives you 96. And the mass will go down by 4. 251 goes down by 4 to 247. Alright, so this number going down to 96 completely changes the element. You don't have californium anymore. You have the element Cm, or curium, and its mass is now 247. And of course you get the helium nucleus also emitted with alpha decay. Again, before the decay started, you had a mass total of 251. You have that still after the decay. 247 plus this 4 of helium gives you the 251. Same process for the atomic number. You started off with 98 before the decay started, and afterwards 96 of the curium plus the 2 from helium also gives you 98. So these totals should be balanced before and after the breakdown. When the nuclei of either alpha or beta or positron or gamma emitters propel their radiation out, what's produced is a new and more stable nuclei. That's the whole point of emitting radiation, is to become much more stable. That's what's indicated here in all 4 of these images. An alpha emitter will give you helium nucleus, which will give you a new element. Mass number goes down 4, atomic number goes down 2. With beta, what you'll get is a new element. The mass number doesn't change, but the atomic number goes up 1. If you have a positron emitter, you get a new element. The mass number stays the same, but the atomic number goes down 1. And for the gamma emitter, you get a stable nucleus of the same element, and neither the mass number or atomic number change. So depending on what type of radiation you're talking about will determine what happens to that mass number, what happens to the atomic number, and whether or not a new element is formed. Producing radioactive isotopes? Radioactive isotopes are produced when you have a stable nucleus that's converted to a radioactive nucleus by just bombarding it, just peppering it with a small particle. And that whole process is called transmutation. So if you were to take a stable nucleus here of boron, atomic number 5, mass of 10, and just bombard it with helium particles, so when you add these two together, this process of transmutation, you get a new nucleus, a new radioactive nucleus of nitrogen, atomic number 7, mass 13. You get this nucleus plus a neutron. Again, like we talked about on the previous slides, mass numbers are equal before and after the reaction, and the atomic numbers are equal. 13 plus 1 gives you the same number as 10 plus 4, 14. 7 plus 0 will give you a total of 7 on this side. 5 plus 2, 7. So nothing is lost in this process of transmutation. So you are really just converting something that is stable into something that's radioactive and new. Right, a Geiger counter. This is a very commonly used instrument that helps to detect forms of radiation, mainly beta and gamma radiation. The way this works is it uses ions produced by the radiation that create an electrical current. If you've ever seen or heard a Geiger counter being used, it makes that distinct clicking noise. The more clicks that it makes means more radiation is present. Alright, next topic is half-life. The half-life of an isotope, or radioisotope, is the time that it takes for 1/2 of the original value to decay. And this will vary greatly on individual radioisotopes. Some are relatively short, some are into thousands of years. It just depends. An example is given here, the radioactive iodine we talked about earlier. So after one half-life of iodine-131, you'll get half the sample of iodine, but also you'll get new element produced, xenon. After another half-life, you're getting less and less of iodine and more xenon. And a way to represent this on the graph is called a decay curve for the iodine-131. Its half-life is 8 days. So after 8 individual days, half of your original sample will be gone. So let's say you're starting off with a total of 20 milligrams of iodine-131. After 8 days, you'll be down to 10 milligrams of iodine-131. After 8 more days after this point, you have half of this sample. So instead of having 10 milligrams, you have 5 milligrams. After another half-life, instead of having 5, you'll have 2.5, and then so on and so on and so on. And you can never get to 0. You can't divide a number in half and end up getting a number of 0. You'll just get smaller and smaller and smaller. Now this table has some half-lives of some common radioisotopes. Probably the most common known one is carbon-14. This is used to date fossils. When you hear the term carbon dating, that's usually what they are referencing, carbon-14 dating. Its half-life is 5,730 years, and the type of radiation it emits is a beta radiation. Now, some of these are really short, such as technetium is only 6 hours for half-life. Radon-222 is 3.8 days. Some are only minutes long. Carbon-11, half-life is only 20 minutes long. Radium-226, 1,600 years. And then potassium-40, 1.3 times 10 to the 9 years. Yeah, so that value would be 1,300,000,000 years. So as you can see, various elements have a great variety of half-lives. Alright, some medical applications using radioactivity. Scanners are going to be used to detect radiation from radioisotopes that are given to patients that can accumulate in an organ or in various types of tissue. A very common example is one we mentioned earlier in this chapter, using iodine-131 to detect issues with the thyroid. And that's what you're seeing here. This patient is being scanned for radioactive iodine-131, and it will show up in various spots within the thyroid gland. Now, radioisotopes that have a short half-life will be used in nuclear medicine because the cells in the body don't differentiate between the radioactive forms of an atom and the non-radioactive forms. And also, once these are incorporated into the cells of the body, the radioactive forms are easily detected because they emit radiation, and normal cells do not emit radiation. So that's what's going on in this image here. The iodine-131 will show up as opposed to, say, regular iodine because it's not radioactive. A tool that can be used using radioactive isotopes is the PET scan, PET scan, positron emission tomography. It will detect positron radiation. Positron emitters with very short half-lives are used to study brain function, body metabolism, and blood flow. And some examples that could be used, carbon-11, oxygen-15, nitrogen-13, fluorine-18. These all will combine with electrons after emission to produce gamma rays, which are detected by the various scanners that your doctor uses. This will help to create a 3D image of the organ. Here's a good example of use of a PET scan. These are scanned images of a brain. The brain on the left, normal functioning brain, and the one here on the right is a brain affected with Alzheimer's. And you can see just by looking at these different colors how a normal brain is much more of a blue area here, and it's much more diminished here because that tissue has already started to decay away. So this is a very commonly used tool to help diagnose Alzheimer's disease. Another commonly used tool with radioisotopes, a CAT scan or CT scan, computed tomography. This is used to help scan organs such as the brain and the lungs and the heart. And you have a computer that will monitor the absorption of 30,000 X-ray beams directed at the brain or at the organ in successive layers. And the differences in these absorption levels are based on tissue densities and fluids. So the example that's given here, someone's brain and skull, solid yellow mass is a brain tumor. And something like this will not show up on an X-ray or not show up all that well because this is living tissue, and you need to be able to detect how well does that tissue absorb or reflect back radiation. So all this other material is going to be regular brain tissue. Right here, which should be similar to this, around it is a solid mass. It's like the outer part of the skull is solid. So that's not a good sign at all. Another tool that's used, MRI, magnetic resonance imaging. This is an imaging technique that does not use X-ray radiation. It's probably the least invasive form of imaging that's available. It's based on the absorption of energy when protons and hydrogen atoms are excited by being induced in a strong magnetic field. And the way this works is the energy that is absorbed is converted to color images of the body. So here's a sample. This is an MRI of the heart and lungs of this patient. And again, the different colors will indicate the different amounts of energy that are absorbed. Thank you for watching our newest video on our crash course in chemistry. We'll have new videos in this lecture series every Monday and every Friday of each week. So stay tuned for our next video in a few days. And don't forget to subscribe to this channel so you can be notified of when our new videos are posted each week.